Part 2 of this lesson on isomerism, we're going to look at what is called optical isomerism. And this is so named because of a physical property, the ability to rotate plane polarized light. We'll discuss that property in more detail in lecture. But that is the only physical method by which you can differentiate these isomers. Okay, now we start out with a term called chiral, and chiral means handed, and chirality means handedness. Your right hand and your left hand are distinct and distinguishable from one another. They are mirror images of each other. There are many macroscopic objects that have this property. For example, gloves and shoes. You have right gloves and left gloves, right shoes, left shoes, and they're clearly distinguishable from each other, and they're mirror images of each other. American cars have this property of chirality. The mirror image of an American car would have the steering wheel on the other side, for example. Okay, next we'll look at the term enantiomers. Enantiomers are non-superimposable mirror images. They're also called optical isomers. Here is the compound 2-chlorobutane, where I've used green to represent chlorine. So chlorine is coming forward. Hydrogen is going back. Then I've made another model. This is also 2-chlorobutane. In this case, chlorine is going back and hydrogen is coming forward. These are mirror images. And we can imagine that you're looking in a mirror. And this would be the reflection, the mirror image. Okay, let's try to superimpose, that is, line up all of the atoms at the same time. Okay, so I have 4 different groups. I have a chlorine, a hydrogen, a methyl, and an ethyl. And if I try to line up the methyl and the ethyl, okay, it is not possible to also line up the chlorine and the hydrogen. If I line up the chlorine and the hydrogen, then the methyl and ethyl don't line up. So these are non-superimposable mirror images. Okay, they have this property because carbon number 2, right here, is an example of what we call a stereo center. And we can identify a stereo center because it'll have 4 different atoms or groups attached. And this has 4 different ones. It's got chlorine, a hydrogen, methyl, and an ethyl. And these 2 mirror images are non-superimposable. Right, so how do we distinguish one from the other? We use something called the RS system. Okay, just like with the ENC, we establish priorities for the groups that are attached to that stereo center, also called the chiral center. Chirality center is sometimes called. We establish priority using the same rules that we use for the ENC, except instead of comparing 2 groups, we're going to compare all 4. based on atomic number, we compare the 4 groups that are immediately attached, 4 atoms that are immediately attached. Hydrogen would be last, it's atomic number 1. Chlorine is 17, so it's highest priority. Carbon is 6, we've got 2 carbons. Then we work our way out to the next one. It's carbon versus hydrogen. So the ethyl beats out the methyl. So this is 2, and this is 3. Okay, so I've prioritized all 4 groups. And this system specifies that the lowest priority group, which in this case would be hydrogen, it doesn't have to be hydrogen, it's just whatever the lowest priority group is, that has to be away from you. Okay, that's important because this is my right, but if you're facing me, it's your left. This looks clockwise to me, but if you're facing me, it looks counterclockwise. Okay, so hydrogen is back, and the other 3 groups are in a clockwise pattern, or to the right, and so this is called the R. So this would be R 2-chloro butane. Okay, for this one, we could either flip it over or we can determine the priorities and realize that it's the opposite. Okay, I'm going to flip this over, which would put the ethyl on this side and hydrogen would be back. Okay, so this time chlorine is 1, ethyl is 2, ethyl is 3, 1, 2, 3. This is the S isomer. Counterclockwise or to the left. Okay, R makes sense to the right. What about S? These actually come from 2 Latin words. R is rectus and S is sinister. In ancient Rome and in the Middle Ages, it was believed that left-handed persons were evil. They were cursed by the gods, so that's what. But originally, it meant left-handed. So those are enantiomers, non-superimposable mirror images. All right, next we're going to look at 2,3-dibromobutane. And I've made a model here. Okay, so this has bromine coming forward, hydrogen going back. This one has bromine going back, hydrogen coming forward, like that. And it has an enantiomer. Okay, so here's the mirror image. The mirror image would have this bromine forward and hydrogen back. This bromine would be back, and this one would be forward. Okay, you cannot superimpose these 2 isomers. They are enantiomers. Okay, so to specify which one is which using the RNS system, we have to do each chirality center independently. We've got 2 chirality centers here, 4 different groups. Bromine is 1, hydrogen is 2, methyl is 3, and then this bromoethyl is 4. Okay, same with this one. You have 4 different groups attached. Okay, so we have to take these one at a time. For this one, hydrogen's already back. So this would be, bromine is 1, it's atomic number 35. Carbon, but the next one out is a bromine. So that would make this whole group here, number 2. And this one would be 3. And I don't suppose it matters which way you start counting for this one, so I'll start from the left here. Okay, so position number 2, here we go, 1, 2, 3, that's counterclockwise or to the left. So this would be 2s. Okay, the configuration at carbon number 2 is s. Okay, for this one, I either need to flip it over or I can determine and simply take the opposite because hydrogen is forward. Okay, so this would be 1, 2, 3, but it's backwards. So this is 2s, 3s. Okay, I can also do a rotation. Okay, where I would bring hydrogen back, and that would switch the bromine and the methyl the way I've got it. So this is 2s, 3s, 2, 3 dibromo butane. Okay. Okay, we list the position numbers twice, both in the configuration and outside of the parentheses. So this means that the configuration at carbon number 2 is S, and also at 3 it is S. Okay, if we work this one out, this is the mirror image. Okay, so bromine is 1, bromoethyl is 2, methyl is 3, hydrogen is 4, it's back. Okay, and so this would be 2R. And I could do the same thing here. Bromine is 1, bromoethyl is 2, methyl is 3. It looks counterclockwise, but you're looking at it from the wrong direction. So it's actually R. Okay, and that should make sense because to go from this mirror image to this one, we had to switch both of these chirality centers. Okay, so those are enantiomers, and we've specified the configuration. Okay, next we'll look at something called a Fisher projection. Right, so this is the first one here. And I'm going to go ahead and erase this. Okay, so this is the 2s, 3s. And for a Fisher projection, what we do is we line up the carbon skeleton vertically. The principal functional group is placed closest to the top, although in this case, the principal functional group would be the bromines, but if you had a carboxylic acid or something like that, that would go up at the top, or closest to the top. Okay, first I'm going to draw a 3D structure. This would be back. Would be forward, like this. Okay, that's a 3D drawing. Then the Fisher projection. Okay, what we would do is for every chirality center, we would blank that out. We would represent it as a pair of intersecting lines like this. Okay, so this is a Fisher projection. Vertical groups, like these methyls, are going back. Horizontal groups are coming forward. Okay, and it specifies that particular arrangement. Okay, so that's a Fisher formula for Fisher projection for 2s, 3s, 2,3-dibromobutane. Okay, the Fisher projection was developed before the R and S rules, and so usually, but not always, the R and S configurations look backwards. Okay, so for this one, bromine is first, bromoethyl is second, methyl is third, hydrogen is fourth. Okay, so that looks counterclockwise, or looks clockwise, sorry. But hydrogen, you can see, is actually forward, and so this is backwards. And so this is actually S. Okay, same way here, bromine is 1, bromoethyl is 2, methyl is 3. That looks clockwise, but we're looking at it from the wrong direction. And so carbon number 3 is actually S. Okay, to make the mirror image for the enantiomer, okay, we would switch both of these. S, 3S. Change the configuration of both of these. Okay, and I think you can imagine if there's a mirror here, this would be the reflection. Okay, what if we change one configuration but not the other? In other words, what if we make the 2R 3S? This is S, so we'll make it R. Okay, these are all stereoisomers. These are mirror images. These are not. These are not mirror images. If I had a right hand and a left hand glove and I cut off one of the fingers on the glove and put it on backwards, for example, then that might be an example of this type of isomer. So these are related as enantiomers. These are related as stereomers. And so are these. These two, first and the third, second and the third are related as diastereomers. Okay, so we can think of diastereomers as being like identical twins. Um, I'm sorry, enantiomers being like identical twins, and diastereomers being like other siblings. Okay, so these are stereoisomers that are not enantiomers. They are not mirror images of each other. Okay. Let's take a look at this last one here, the 2R3S. And let's make a model of the mirror image of it. I'll do that on this side over here. To get the mirror image, I switch the configurations of both of these. So that's a 2R3S, so this would be the 2S3R. I switch both of those. Okay, so let's make a model of both of these. Okay, here is this one. Here is the mirror image. Looks like this. And it turns out that when we line these up, they are in fact superimposable. We can line up all four groups at the same time. And so these are superimposable, so they are not enantiomers. Okay, so how are they related? They're the same compound. And the reason that these are not superimposable, not non-superimposable mirror images is they have a feature called a plane of symmetry. Okay, that runs through here. Also called an internal reflection plane, internal mirror plane, where half the molecule is a reflection of the other half. Okay, this is a very common reason for excluding optical activity. And this particular type of compound is called a meso. And meso is defined as an achiral diastereomer. Okay, we saw that it was a diastereomer. It was not a mirror image of the other stereoisomers. It is achiral, meaning not chiral. So in other words, it's identical to its mirror image. A meso has to have stereocenters. Okay, to merely say something is diastereomer because it has a plane of symmetry is not correct, because many compounds have a plane of symmetry. Okay, for example, cyclopentane. Cyclopentane has multiple planes of symmetry, this way, in the plane of the ring. Okay, but it's not a meso. It doesn't have diastereomers. There are no chirality centers. A meso compound has to have at least 2 chirality centers. And you have to have at least 2 chirality centers in order to have diastereomers. right, the last question is asking about cis and trans 2-butene. And it is asking if those are diastereomers. Trans, cis. Okay, definition of diastereomers, they are stereoisomers that are not mirror images. Okay, these are stereoisomers because the three-dimensional arrangement in space is different. Okay, are they mirror images? Okay, that's what you need to decide in determining whether these are if they are stereoisomers, are they mirror images? Okay, so that will determine whether these can be considered diastereomers or not. Okay, one thing I did not do was the Fisher projection of 2-chlorobutane, the first chiral compound we looked at. Okay, that has just one stereocenter. So you draw one pair of intersecting lines. Then we have a methyl that's back, and then we have an ethyl. We don't draw a pair of intersecting lines here because this is not a stereocenter. Okay, so this one has chlorine on the right, or chlorine on the left, hydrogen on the right. Okay, and then the enantiomer would be like this. Switch these two groups. Okay, so this would be the R, and this would be the S.